So today we're going to use a number of open source tools, several of which are contained within this diagram, such as Kubernetes, Kafka, Node.js, 3Scale, and Scupper that Ben's wearing the t-shirt for. With Red Hat, everything that we do is open source, and the entire solution today is available on GitHub for any of you to take, run as is, or customize for yourself. This kind of open source ethos is basically a fueler of innovation for any number of use cases across the public cloud, the private cloud, and at the edge. So now with the tool set that Ben has empowered me with, I'm an empowered developer with the freedom to deploy and to connect my applications in a locationless manner. What am I going to do with this capability? So let's actually see this in action. And this is the challenge that I'm trying to solve here in this demonstration today. We want to detect activity at the edge. In our case, it's a human that's going to be feeding into my webcam. It's myself. And we want to be able to use an AWS-based AI model that's going to interpret that in real time, that image coming from my webcam in real time, and it's going to basically create a count of the number of times that it saw a human or anything else we'll call background. And it's going to display the count in real time on a dashboard on our website as it is today. But the solution is easily extensible because we're training an AI model with our images, but could easily be modified to detect things that might be of more use, like a person that's on a train track at a train station, imperfect pills in pharmaceutical manufacture, equipment damage at a remote cell tower, or even sharks in offshore drone footage. So it's really highly extensible and customizable. But it sort of begs the question, why did we choose this case for application connectivity? Well, it's a few reasons, really. This is an increasingly important challenge nowadays, making sense of the enormous amount of data that's being generated at the edge. And it calls for more connectivity options that is available using our traditional RESTful APIs, considering edge connectivity, considering AI model usage, and considering multi-cloud. So we need an expanded tool set to cover all these requirements. And it's not a trivial problem, actually, that we're trying to solve here today. A funny situation occurred in Scotland a couple of years ago, a similar use case to what we're doing today, where an AI model was trained to follow the ball, and the TV cameras would go wherever it thought the ball was. But it wasn't trained well enough, and the model thought that the linesman's head was the ball. So the camera followed him instead of the actual game, and there's a lot of interesting comments and reactions from people at home who are trying to follow the game. So this is actually a high-level architecture of the first part of our demo, using my webcam on the left to capture an image through my laptop. And I need to connect my edge-based application that captures those images to my AWS application on the right that's going to consume those images in real time. For each one, it's going to ask the AI model what's in that, and then it's going to write those out to object storage, and then it's going to be interpreted by a dashboard on the right that's going to report in real time. And to make that connection between the edge and AWS, we're going to use Kafka, and we'll explain why we made that choice shortly. So now what we're going to do is start to drill into the individual components of the demo. So as you can see, we're going to be feeding in film images into the webcam that we're interested in, either person or anything else we'll call background. This is a lightweight Node.js application that's running in a container. In our case, it's running on Kubernetes that will be running at the edge. Then that application, that Node.js application, is going to fire up the images via Kafka, cloud-based Kafka, and it's going to be picked up by a Kubernetes-based application running on Amazon Web Services that then will do a few things. It will first off ask that AI image via ask that AI model via a RESTful API what is contained in that image. It's going to report back, and it's going to write a count in real time of what it's finding to object storage. That's then going to be easily consumable by clients that are interested. In our case, a dashboard on the right that's going to report in real time. Let's now actually switch over to our live demo. So here on the left is my edge-based application. See, it's a Node.js application that is going to capture the images in real time for my webcam. So I'm going to open up that application here. And I'm going to allow it to access my webcam. I'm not going to start to capture images, but when I do kick this off in a moment, it's going to send them up to Kafka. So,
you want to talk about the architectural choices for this edge?
Sure. So we're using a lightweight container-based Node.js application to pull the image from webcam and push to Kafka. We use a containerized application for its simplicity, because all the dependencies for that application are encapsulated within the container. So there's no difficulty in building that application. And for its flexibility, because in low power environments like we often have at the edge, it can use a lightweight runtime component like Docker or Podman, or it has the flexibility if there's a Kubernetes cluster close to that location in a data center or in a public cloud, for example, we could also use that, and that's what I'm actually using. I'm using Kubernetes there. All right, so next we're going to move across to our cloud-based Kafka service. So we have, this is a Red Hat hosted Kafka service that's available to anybody to sign up for free. And we've basically created a Kafka cluster here called Kafka Rocks. And we also have a few things here like our topics. The topic that we're going to send to is this video stream here. We can also apply consumer groups, properties, and schemas to this. So it's a very useful vehicle for sending our, for getting our images up to the cloud from the edge.
So rather than sort of the camera steering back, you've sort of chosen to send time snapshots back?
Indeed, yeah.
Was there any reason for this?
Yeah, so my webcam is going to generate 30 images per second, but I'm only actually going to send up 1 per second because I'm not interested in what's contained in every image. Rather, I'm interested in detecting a changed situation at the edge, a new fault in my equipment or a shark that's swimming in the sea. So that's why I basically only send up 1 in 30 because it's going to reduce the amount of compute and storage and associated costs. And we chose Kafka as the vehicle here to send the data from the edge rather than a RESTful API because it's a more appropriate choice for this use case. It's useful for kind of fire and forget situations because at the edge, we're not interested in getting a response like a RESTful interface because we're not going to interpret the image at the edge. It's going to be interpreted on our AWS application on the cloud. We also want to, all we want to do is, we don't care if every single image doesn't get there. We don't need guaranteed delivery. We just need basically to be able to detect changes. And also with Kafka, it enables multiple consumers that are interested in subscribing to this feed of data to consume that data. Processing engine, a reporting engine, an alerting engine. And also Kafka is quite easy to connect to from the JavaScript at the edge or any programming language at the edge. So that's why we chose Kafka as that connectivity vehicle between the edge and the cloud. All right, so now we'll move over to the component that is the AWS-based component here that basically is our controlling application. So this is our consumer. It's basically our controller that pulls the images from Kafka, sends every single image across to our AI model that a component called Selden wraps behind a RESTful API and then writes out the results of what it finds to object storage. This is MinIO, a lightweight object storage implementation. And we have a dashboard then, another Node.js application that's going to detect in real time what's happening at the edge. So we chose Kubernetes as the platform to run this AWS cloud-based application because it provides high availability and scalability. So in response to extra demand, it will auto-scale up. Humans don't need to do that. It facilitates with OpenShift, the Red Hat Kubernetes distribution, it facilitates multi and hybrid cloud because it's an identical experience everywhere. And it's a single platform that can house all of our workloads. It can house our AI, our APIs, and our applications. Yeah. So in terms of why we use this Selden component, it can be quite not a trivial matter for an application developer to make a call to an AI and to get a response back or a prediction back. Selden is a really nice open source component. What it does is it wraps the binary that is the container, it's built by TensorFlow, into a container, and then it exposes a RESTful API. So very simple for application developers. It's an interface that we all know as developers, and making that much more consumable and easy to move fast, really. The other API that we, if I go back to my diagram, that we're using here, down here is this MinIO one. It's an object storage-based implementation.
So why did you use object storage?
Well, a few reasons, really. It's simple to read and to write over a RESTful API. It's flexible because there's many implementations of that S3 interface. So the same code base could be used to call MinIO, could be used to call Amazon S3, could be used to call Ceph or other implementations. So very flexible, and then doesn't require a rewrite of our code that calls that. It's highly scalable, particularly on public cloud. And in this use case, depending on the number of cameras that start to get connected up, the actual amount of data that could be generated could explode. And we want a solution that is, auto-scalable like object storage provides, and also it's very cost-effective. So it was an obvious choice there. All right, so now let's actually see our AI model in action. So what I'm going to do here is go over to, if I can point the camera at myself, I'm going to start to capture here. So you can see over on the right, it's capturing 1 in every 30, 1 every second. And it's pushing that up to Kafka. My AI is being called, the results being pushed to object storage, and then this dashboard here should start to detect the fact that it's a person, because the image of me is being sent up. And you can see that that's working. The count of the times that it detected a person is going up around once every second. So now what I'm going to do is go back over, and I'm going to turn the window on my webcam, and now go back to my dashboard, and you can see that instantly it's no longer detecting a person, it's detecting in real time the fact that it can no longer see a person because I blocked the window, and it's now seeing background every second. So that's really cool. It's capturing in real time. It's a trivial use case, but it could very easily be applied to a real world problem.
So we have a lot of north-south traffic flow here, but what would you consider for connectivity for east-west, for example?
Okay, well, there's a couple of considerations here around sort of management, including east-west. Our APIs that we're using in here, the Selden for the AI and the object storage for the count of what's happening. These are internal-facing APIs in our use case, but if we wanted to expose those to other teams within the organization, or to our partners, or to our customers, and we wanted to get some control and some visibility into those, then we should consider an API management solution. Alternatively, we've got a small number of services that are involved in this solution here, but if that started to explode into multiple microservices, and we wanted to gain control and visibility, if we wanted to get authentication, authorization, if we wanted to encrypt the traffic that's going from service to service, from east to west, then we should and we could consider service mesh solution like Istio, for example. So these are kind of extensibility options that would be very much available to us. So just to close out my section, we took two APIs, and we have two APIs that are involved in this solution here, and let's just show them in action. First off, the MinIO one here. This is a simple call here to my RESTful API, and it's a simple get that returns back the count that corresponds to what you saw, the number of times on the screen encountered a person. If we wanted to apply API management on that, we could very easily do that. This is 3-scale API management, and this is the Open API interface under the Active Docs banner here, and we could, using the 3-scale solution, we could apply, for example, authentication and authorization by using an API key to control and to get the visibility into that traffic for using API management. And then the other API that we used today was the Selden-based API here that's exposing my AI model. Now, you can see this is not so friendly for traditional API use case, and I'm going to show you an alternative in a moment. This is, can everybody know what every one of those is?
Black.
Yeah. So we got obviously a multi-dimensional numeric array that shows the RGB, the red, green, blue, of every single pixel that's in a photo. And we can make that call. And this is actually a real image. And my Selden-based API, whenever it comes back, returns that that's not a person, it's a background. Of course, we could, similarly to before, if we're using API management, we could use that as the testing tool, the Active Docs or Open API interface in the same way. But really, a better choice than this Open API interface, because it's an AI model, is to use a development or authoring environment that data scientists use. This is Jupyter Notebooks. So this is actually, it's on GitHub, and any of you who want to use this can use this to train your own models. This is the inference URL that was used within Postman. And it's more of a suitable tool, really, because you can actually output what the image is. So rather than that huge multi-dimensional numeric array, we can see a picture of what we're asking the AI to detect. And then we apply some encoding here to do that conversion, wrap it in some JSON, set some headers, and do a post here. And this image that we have up here is actually the same one that we used in our Postman a second ago. And you can see that this is a better way for testing out these AI-focused, particularly image detection-focused APIs. So at this point, I'm going to hand over to Ben. And really, what we're going to address here is the situation where, say, our organization have decided that we want to move our dashboarding and our reporting and our alerting off of AWS onto another cloud, onto Azure. How easy is this? How smooth and seamless can we make that transition? Because we ideally don't want a huge change control process. So Ben's going to talk about that.
As soon as I get connected.
Just got a quick question.
Yeah.
So for the Kafka, when you go to the dashboard, this triggers the consumer, or the consumer is already consuming the data from Kafka, and you are just calling the API when you do the start at the dashboard.
The consumer's running all the time, and it's basically pulling anything new that's pushed up to that topic.
Yeah.
So in our case, when we hit start, it started to fire up 1 image per second.
Yeah.
Then landed on the Kafka topic, and the consumer detected that there was new images there, pulled them down in real time, and then asked the AI. So it's
just the subscription to the topic is enough for the Kafka to be consuming. Yeah.
Exactly.
Yeah.
Yeah, exactly.
All right.
You don't need any kind of webhooks or anything, it just can run all the time. Any other questions at this point on what I just showed? All right.
Thanks.
Yeah.
So now for a situation, I want Azure to host my front end, including the dashboard that you saw with Tom that sort of had the results of the image prediction. But I don't want to move the entire system, as typically my AIML service and my data is anchoring me to a certain cloud or location. Now, normally I might need a whole change control process, the likes of a VPN or security, and that would take a very long time in an organization and have to work across multiple teams, across multiple technologies, and it's hard to determine the right choice. Instead, I want to introduce a technology option that will, 1, provide a secure network and means to connect that is compliant with my enterprise security. 2, is fast and simple and easy to implement. And 3, something a developer could use and still, coming back to that developer freedom, maintain that freedom of choice and with what protocols we connect with. So we saw the diagram before where everything in the back end was on AWS. So I'm going to take the dashboard from AWS and host it in an Azure environment. Now, what technology I'm going to use? Scupper, like my t-shirt here, is the technology that will help me meet those needs. It's a service interconnect, enabling secure communication across Kubernetes clusters with no VPNs or special firewall rules. And with Scupper, your application can scan multiple cloud providers, data centers, and regions. It's really simple to set up, and I'll be showing that. It's a single command line to install. It sets up the Scupper router and within a single namespace within a cluster. And once connected to another namespace in another cluster, will provide that seamless visibility and connectivity between the Kubernetes services. So it really gives the app owner that freedom, control, and agility. You don't need to be cluster admin, you don't need new firewall rules, and you don't need to change your app. It's secure by design, in that it secures data with mutual TLS, enabling zero trust environments, and is connecting applications rather than the hosts. However, it will only expose the services that you specify. And now this Scupper project is new, but the tech which underpins the connectivity is a mature product, and it's had 20 releases since 2017. So let's start to have a look at what we... Okay, so I've got the dashboard here. This is the original dashboard, and I can go to that and see that's still reading from the queue. Okay, so what I'm going to do now is spin that dashboard down. And I've already provisioned the dashboard in my other arrow cluster, and that is here. So I've got a different OpenShift Kubernetes cluster here. I've got my dashboard, but it's currently not connected. So and the dashboard is here, and then I can go and observe that. So it's just one of one pods here, and then I'll spin that down. So I've spun it down in AWS. Now, what I need to do is I need to now install Scupper in the environment. So I'm going to just make sure I'm connected first. I'm on the project in my Azure cluster, and to install Scupper, I'm going to do a Scupper init.
So Ben, can you kind of give us a recap what does Scupper offer over and above a VPN? Because they've clearly got ways to connect into...
So essentially you're setting up two routers in different endpoints, and these are in different namespaces connecting MTLS between them. Essentially, you don't need that hard VPN backbone like you normally would. So that's starting to install. So we will see now actual Scupper pods being spun up here. So you can see we've got a Scupper router in service. Now I will just have to go and get the login details secretly. So I'll log into the console. Do that. And if I go into the Scupper dashboard, so I'm now logging into the Scupper dashboard on my AWS cluster. So this gives me a view of the deployments that's within my namespace here. You can see I've got a number of the deployments Tom was talking about there. But in particular, my dashboard needs this service here, MINO, from the S3 API. Okay, so if I go to the network view, I can see I've just, all I know about is myself at this stage. So I go to the Scupper on the other dashboard. So I'm logging in. This is the Scupper on the arrow. And this is where I've got my deployment. It's in the dashboard. This is where I can choose to expose it. So now, if I say I want to link a remote site, so I can do this via the command line, but for today's purposes, I'm just doing it via the UI. So I've copied the token to the clipboard, and that token details pretty much everything you need to connect. And I'll say use a token, user token from the clipboard. So after a few seconds now, we should start to see them connect, and it's a fairly seamless connection. So now I'm in my Azure cluster. I'll go to the dashboard. If I start, I'm not getting any data back yet because it's actually not, that service is not exposed. So although the scupper's there, it's connected both namespaces. So as soon as I expose that service, and this is not just HTTP traffic today. With Scupper, you can use any TCP-based traffic. So think of about, databases, how you want to connect them from one cluster to the other. That traffic can work as well. So I've exposed that. And let's go back to the dashboard. And you can see now it's starting to receive that data. So simply, if I show you what's in my the pods running in my front ends now, you'll see I've got the dashboard running, and I've got the Scupper router and controller running. Within my services, I can see my dashboard, I can see Scupper, but I also can see the service, and that's how I'm directly talking to indirectly sort of the other cluster. So I'm still using the service name, and I haven't changed my config on my application at all. And that service has been exposed by Scupper, and Scupper has represented that as a service in this namespace. There is multiple ways. Scupper can represent Kafka as well. Sometimes it sort of builds a proxy within that namespace to connect, but if you go to scupper.io, and I recommend you do that after this, you'll see all the use cases it can apply. So just come back to Scupper. So, you've seen it, it's simple to set up, it's secure by design, but it's really such a lightweight technology. You can connect anywhere. Because if you want to design a distributed application, it's easy to set up. I mean, you can easily sort of work it with on a VM, and that's sort of, those features are being developed in the open source project as well. But it's really not simply just a point-to-point technology. It's a smart network with smart routing, redundant pathways providing that high availability connectivity at scale. So we've just seen point-to-point today, but really it's about setting up a redundant topology, and it will route traffic, if one of those nodes is down. And it can even do that smart-based routing. So if you want to do cost-based routing, you want to direct your traffic to one cloud over the other, you can assign costs per node, per each node, so it will do that as well. But really, the most important thing to take away is your applications don't need to change. And whether you're using REST, gRPC, JDBC, TCP, that traffic can navigate across that Scupper link. And you really have that portability. You can't really have portability without addressing this connectivity question. So basically, going back to sort of the diagram and schematic, that Scupper layer has enabled me to lift and shift one of my components, rather than everything, into another Azure cluster. Any questions at this stage? I'm happy to take questions.
So you have to install the DNS solution works in this when you have a Scupper. Does it mean that the traffic is coming into the AWS and then routing the Azure to the Scupper proxy?
Yeah, so Scupper basically intercepts that service call. As a networking person, I can get someone there to give you the underlying answer for, but it's essentially managing that service name. Any traffic going to that service, Scupper will intercept and then send it across.
So service-to-service communication within or across Kubernetes is not exposed to the outside world at all, and that is still the case. So our dashboard engine is not exposed in any way. It just uses that service-to-service tunnel, if you like, and that tunnel is now extends across clouds
Scupper was installed on both classes individually.
Scupper was installed in both. Yeah.
Yes, yeah. So you had to run the command twice.
Yes. So I had it already installed in, pre-set up in the Azure, but it was essentially that Scupper init, that project, and you can, with Scupper, there's a number of available commands. You can do everything via the command line via APIs CLI. Expose, delete it. It's easy, simple delete as well. So
So Scupper is basically, effectively got those scripts on the inside, and as you invoke it, you point it to your cluster you wanted to work on, and just automatically puts those things in there, spins it up, creates the containers, and you're off to the races.
exactly. Design your microservices the way you feel fit, and move your components without changing that config really.
So it reduces the need of someone actually going in and typing in the YAML to build the image immediately. It's just they're ready to go. Awesome, wonderful.
Yeah, you still sort of deploy it on wherever you want, but to connect them, this is a key component to help you really achieve that multi-cloud.
Yeah, all good. Thank you.
Or on-premise. Thank you.
So the Scupper, does it can deploy inside the Kubernetes or outside of the Kubernetes?
Scupper is sort of Kubernetes focused, although I know there is sort of gateways to that I've seen on the website where it's still sort of some work in progress, but you can have Scupper gateways sitting on a VM, for instance, and working with the Kubernetes cluster. So if you had a big database, the use case would be having a Scupper gateway and being able to have if you've got a database you can't move, whatever cluster you want to sort of connect that to, you could do that. Yeah. If you come to the demo booth and stand, I can show you how sort of the JDBC connects. Simply, this is just a Postgres web, but I'm actually connecting to a database in a different cluster. So JDBC is going through that Scupper link. It simply wraps that TCP traffic up, sends it across, unwraps it at the other end, and then receives it. And so
would the same thing happen with something like Microsoft SQL commands as well?
yes. So any TCP, it should be supported.
So let's say you've got an application sitting in the cloud because you want to use their compute because it's a lot more efficient to get that up and running. You've got Scupper on-prem and off-prem to link the two, and you route the traffic into on-prem because that gives you direct access to a database that's hosted on-site. Scupper obviously is providing that link so you can get the data backwards and forwards.
Yes.
So it saves you the need of having to provision an Azure database, for example. You can just use on-site because customers want the business that they're interfacing with to manage the data rather than a third party.
Absolutely. And if you come back to that locationless question, does it really matter where it sits? As long as it's exposed, that service definition is there, I can connect to it. One of the real life use cases is we're talking about how can I migrate to the cloud, and I can do that incrementally with Scupper. I don't need a big bang approach at all. Yeah. Awesome. So, Tom, I'll pass back to you.
Sure. So here you can see, obviously we're working with 100% open source components, but here you can see some of the actual Red Hat implementations of those open source components. We actually used the Red Hat ones, but it could be used on Kubernetes equally. And we want to give a plug to our Senior Director, Mark Cheshire, who's going to give a talk, a higher level context of application connectivity tomorrow at, 2:05? Yeah. As we say, everything we did is available on GitHub. Please come see us at the Red Hat booth if you want to dig into the actual demo or talk to us about application connectivity or integration or any of the open source components you heard about today. So that's it. Thank you.
Thank you very much.